Okay, so we're going to talk about HPLC column basics and also characteristics. Okay, and today we talk about hardware, different types of columns, column length. DC stand for the column ID or inner diameter, and some of the support type, meaning that the particle size and the pore size. Okay, so this is a series of 4 webinars on HPLC column. So it's going to be starting this week and then for 4 consecutive weeks. So the first week is HPLC column basics, as I mentioned about what we're going to talk about, hardware types, different modes that I mentioned. Next week would be bonded phases and also the Van Diemt equations. And we talk about silica bonding chemistry, residual cyanols, the need for high purity silica, and also a very important equation called the Van Diemt equation. The third week would be on the modern trends and also how do we select columns. Okay, so there's a trend towards a shorter and narrower column. So today picking the right column is very important. So there's a big trend in the modern HPLC practice today of using very short column. Not too long ago, the column length, standard column length is 25 centimeters. Today is more like 5 to 10 to maybe maximum 15 centimeters because the particle size are getting smaller. Very important to pick a silica, which is called high purity silica, right? So most of the modern columns are made from high purity silica, and we would define what that means. And some of the modern bonding chemistry and what some of the selection guide for pharmaceutical application and other application. Finally, in the 4th week, we can talk about some recent column development, such as hybrids, charge surface hybrids, HELIC. HELIC stands for hydrophilic interaction chromatography, right? So sometimes you do need it. In most cases, reverse phase is sufficient. And it's also the best and the most reproducible. I want to mention something called SPP. I would continue to mention that. That's really something that you should be aware of. SPP stands for superficially porous particles, something that you really should be using today if you're developing a new method. Also, chiral separation, and MCC standing for mixed mode chromatography. Okay, like everything else in HPLC, we have our own set of lingo or jargons. And in order for you to be considered an insider, it's like if you're in IT, in information technology, you have a set of jargon that people understand each other. So it's very nice to kind of understand some of the terminology and some of the acronyms, some of the short abbreviations, right? So some of, we have actually mentioned some of these before, right? So column support, it is the spherical porous material used in this column packing before bonding. Typically, we deal with bonded phases, which is column supported with a ligand attached to it. Most of the ligand are hydrophobic to have very weak interaction. So after the bonding, we call it stationary phase, which is support modified with bonded groups. And like we mentioned many times before, the most important column is the C18 column. That is going to be satisfy the majority of your needs, right? So if you have to develop a method, most likely you would use a C18 column. At least I would say 50% of the applications are using C18 columns, particularly in pharmaceutical analysis. Some of the other acronyms are L stands for length, particle size, dp, pore size, D sub C is column ID, radius. H stands for a plate height. We would define that later on, which is the same as HETP, which is called a height equivalent to a theoretical plate, right? So we talk about a plate later on next week. There's something called the minimum plate height, which is the best operating condition you should operate your column in at the minimum plate height to give you maximum efficiency per unit length. And that happened at something called the optimum velocity. N stands for the plate count. K is retention factor under isocratic condition. Alpha is selectivity. And it's a ratio of the two retention factors. Resolution is what we're going after, right? Is how the degree of separation between two adjacent peaks. V sub m is the void column. T sub 0 is the retention time of a void marker. F is flow rate. Gradient time, we talked about that extensively. It's really a powerful parameter that you can change, particularly if you have a multi-segment gradient. You can do a lot of method development using gradient time and the gradient segment. You can do a lot of higher resolution for your complex separation. Peak capacity is the number of peak that you can accommodate in a chromatogram, is P sub C. Delta P is the back pressure. Peak width at the base is W sub B. Peak width of half height is the width of the peak at half 50% of the height. Later on, we define what is a hybrid. A hybrid is a modern particle, not made purely from silica. Most material support is silica. A hybrid is have an inorganic part, which is silica, or basically silicate, and also an other organic moiety. So we talk about hybrid in the fourth week. SPP, superficially porous particle, something that you really should be using today. It's also called core shell or fused core. Okay, this is a quite important slide. Okay, it talks about different type of columns. Right? Some of these are not something that you should be aware of, but it's not something that you would actually use. So what is a HPLC column? Is typically a stainless steel tube. It's a cylinder filled with packing material. The majority of the packing material is silica, right? That's the way it's going to be. Okay, a lot of people try to find something better. Silica is not perfect, but so far it is the most common support. So nothing actually does better than silica at this point. HPLC column can be categorized in many ways. You can use column hardware, which is standard. By standard hardware, we mean a column that you are familiar with. You can see the column is made from 316 stainless steel with 2 end fittings. And then you use compressional ferrules and tubing to attach it to it, right? There's also something called cartridge column, right? Cartridge column is kind of coming back, but we explained to you what does a cartridge column buy you. Probably not too much today's world, but it is coming back for micro or nano LC. Other column material could be PEEK, particularly if you're doing ion chromatography, if you want to have a metal-free environment. Besides stainless steel, titanium actually is more corrosive resistant, right? So some of the bio-inert system are using titanium. PEEK is actually problematic because it does not have a lot of pressure rating. So sometimes we use PEEK line stainless steel. For nano LC or micro LCs, often we use fused silica. Okay, we talk about chromatographic mill. Reverse phase is the most prevalent. There's also normal phase ion exchange. So you can categorize columns by different mills. Also, dimensions are very important, right? So everyone here focus on analytical, and that's from 2 millimeter to 4.6 millimeter ID. For those of you who are actually doing preparative or semi-preparative, the column are much larger. There's a technique called Fast LC. Actually, I was part of the Fast LC team at PerkinElmer in the 1980s. I would say Fast LC is mostly superseded by HPLC in today's world. There's also names called mini bore, narrow bore, micro bore, and I talk about some of these terms later on, and micro and nano LC, which are also called capillary LC. And most of the support type are silica, but it could also be a polymers, a hybrid. It can be totally porous. It can also be SPP. You can define column by pressure rating. In today's well, most laboratory have a mixture of HPLC and UHPLC, right? UHPLC definitely prefer. They have much higher performance, it's more costlier, but that's a way of the future. You can also do medium LC or low pressure LC, mostly in the preparative arena. So this is chapter 3 of my book that talks about some of these column description and types. I'm not going to spend a lot of time on this one, right? So this is just some common column packing characteristic, right? So mostly it's silica, the bonded group, C18 is most prevalent. Particle size, I'm a strong advocate for sub 3 micron, and I explain my rationale a little later. Today, you really should not use 5 micron and 10 micron for your analytical for your analysis work, because there's really no advantage to be gained by using 5 micron. So either 3 or sub 3. Occasionally, we would go down to sub 2 if you really need the speed. However, for quality control application, which the majority of the people engage in something quality control, which you need higher reproducibility, then sub 3 probably is more QC friendly. Pore size is important. So I would say the nominal pore size for small molecule organic would be about 100 angstrom. If you use a large biomolecule, then you should use something larger pore size, such as 300 angstrom. And surface area are pretty high. So typically 1 gram of silica have surface area as much as 200 meters square per gram, which is a huge amount of surface area, as much of that of a basketball court. See, 1 gram of silica, 1 gram, which is not a lot, have a lot of surface areas. Okay, so this is the slide showing the characteristic of a typical analytical HPLC reverse phase column. And those are some of my, what I call the default, right? So if I want to do a stability indicating assay, most likely I'm going to use a pretty long column to give me a good separation. So it would be 15 centimeter times 3 millimeter ID. I'm a strong advocate for something which is 3 millimeter ID. I think it's a good compromise between sample size and QC application type of. If you use 2.1, it's good for high throughput screening, but perhaps your injection size is a little bit too small, right? So 3 is a good compromise. Big fan of 3 and mostly sub 3 micron. Sub 3 means 2.6, 2.5 micron materials. Typical flow rate, the default is kind of about 1. It's a good compromise, right? Because if you have a 1 liter of mobile phase, you can use it for over 24 hours in general. Most of the typical range is 0.5 mil to 2 mil. It's really not a good idea to use 3 or 4 mil because then the technique is not green, right? So why waste our solvent and spend time getting rid of it? Sample loading is important for sensitivity, anyway from 1 nanogram to 1 milligram. The default kind of standard is 1 microgram, right? But you know, it's whatever is needed to get your sensitivity. For HPLC, the operating pressure is this range. Maximum is about 6,000 psi, or in some cases 5,000 psi. Typically, we're running about 3,000 to 4,000 psi, right? So it's nice to use as high a pressure if you can do. For UHPLC, typically we go up to 10,000 psi or 12,000 psi. Okay, for plate counts, anywhere from 4,000 to 20,000 plate count, right? So 20,000 plate count is kind of the default benchmark for a high resolution separation, right? So that is a 15 centimeter column packed with 3 micron particle would give you something about 20 to 24,000 total plate count. The equation we will describe later on, right? So the plate count is equal to the length of the column divided roughly by 2 times the particle size. The cost of a column typically would be, I would say, about $800 US dollar. It is pretty expensive, right? Particularly for research institute for university, right? For pharmaceutical company, usually is considered as a consumable, right? So they charge a lot for their drugs, and $800 is typically not a big issue. A column lifetime, I would say 1,000 to 5,000 injection. The lifetime is getting better. I would say typically, if I need a number, would be something like 2,000 injection. And very much depending on the how clean is your sample. Okay, so here's a schematic of the cutaway of a column, right? You can see that a column is a cylinder, and at the end of the column is a set of frits. Frits is a porous frit material. They are made from stainless steel, pressed together with a nominal porosity of 0.5 micron. Okay, so you need something to contain the very small particle. Make sure they don't fall away. Okay, and then you have two end fitting, right? These are typically swage lock fittings, and use a compressional nut with ferrules. Now today we don't really use stainless steel ferrule for column connection anymore, right? We use a one-piece peak ferrule. If you use HPLC, you probably the best way is to use a upchurch, a single finger type nut with integrated ferrule. It's about $1 each. It's a very easy way to connect column, right? So that really obsoleted the way of using cartridge column, right? In the 80s, there was an innovative column design by Bob Brownlee. He set up a company in California. He designed a set of cartridge column, which is very, very nice. And actually, you can do finger type connections without using a stainless steel compressional ferrule. So at that time, it was really nice. Today, there's really no need for this type of thing because we can use finger type ferrule even for HPLC. So these are column. This column says waters. These are two waters column, right? You can see that they come in different form, but they are all basically the same type of fitting, right? Yeah. So they don't use swage lock fitting. Waters make their own fitting. They have different insertion depth, and their fittings are not interchangeable with other columns manufacturer, right? So you have to be cognizant of that. So another reason that you should use a finger type fitting, then you can use both types of columns. Column dimensions are really important, right? Particular length and column ID, right? So here are some of the ramifications, right? Because the length determines column efficiency. Because if you use a longer column, you have more plate count. And however, if you use a long column, the analysis time also become longer. And the pressure drop, the delta P also get longer. So the plate count is equal to length divided by the peak height. A column inner diameter is also very important, right? Typically, the outer diameter is a 1/4 inch OD, outer diameter. And the inner diameter, the standard is 4.6 millimeter ID. However, as I mentioned, you shouldn't use that. You really should be using a 3 millimeter ID column for QC application. Column ID are very important, right? They control the flow rate. It also control the mass sensitivity. The column void volume is equal to the empty column, right? Because it's a cylinder, so the empty column is pi r squared L. And then the void volume is about 65% of the empty column, right? Now, what is the void volume? The void volume is the column, the liquid, the volume occupied by the mobile phase inside the column. Since you have a silica porous particle in there, right? About 35% of the solid silica particle are the solid which is not permeable to the liquid, right? And so approximately 65% of that column volume of the cylinder is occupied by the liquid, right? So that is the combined total of the interparticulate volume between the particle and interstitial volume inside the particle. There's a lot of liquid inside the particle. Okay, this is an important table. It came from the chapter 3 of my book, right? So here are the column type, right? Some of these names are not standard, right? So it's just kind of a convention. So typically conventional HPLC column is 4.6 mm ID. Now there's no regulation that you have to use 4.6 mm ID. It just turned out that in the 1950s and 60s, if you try to get a tubing, a precision bore stainless steel tubing at a 1/4 inch OD, the standard tubing inner diameter is 4.6 mm ID, and this actually is a good match for the flow rate. So the older column, this is really a pretty ideal ID. Today, because the HPLC getting better, the flow cell volume is getting better, the inner diameter of the connection tubing is smaller. We really should be using 3 mm ID, right? There's no reason to use 4.6 anymore for analytical, for analysis purposes. There's also something called the mini bore or narrow bore, which is 2.6 mm ID. It's also pretty standard for UHPLC to have this one. It is kind of small for QC application, because when you're using a small ID column, you have to inject very small amount, right? Such as 1 or 2 microliter of your final sample. And that means you really have to have a UHPLC injector or auto sampler do a good job, right? So for QC, we like to inject a little bit larger volume for higher precision. And then we have micro bore column, which is 1 mm ID, and then capillary column, a micro LC, which is 0.5, and nano LC, which is 0.1. When you get to micro and nano, it's very difficult to use UV detection, right? So typically you have to use mass spec detection. Okay, a little bit of something called mass sensitivity, right? What is mass sensitivity, right? So if you have very small amount of sample, let's say you're interested in the proteomics of an insect's eye, right? You're interested in a protein on a fruit fly's eyes, the total protein, right? You have so little sample, right? If you use a regular column, which is 4.6 mm ID, and you inject, and you cannot see it by UV detection because there's too much dilution on that small amount of sample. Your sample limited. However, if you use 1 mm ID using a micro bore column, this is an old slide. Came from Perkin-Elmer in the 1990s. Using low flow rate, you can get much higher mass sensitivity, right? So now this is not really concentration sensitivity. Most people would like to see lower concentration. Using a larger column does not give you less sensitivity because you can also inject more, right? So we are talking about when you have a limited sample size situation. You want to have higher mass sensitivity by injecting the same amount. So definitely you get higher peak height or sensitivity by using a smaller column because you have less dilution. Okay, effective column length, right? So here is a set of figures from Agilent Technology. Okay, so I have a bunch of column, right? So some of these are very short column, right? This is the 15 millimeter column, not 15 centimeter, right? So a very short column. Plate count is only 2,000. You can see that you have really fast LC, fast liquid chromatography, but the resolution is not good, right? There's also a little bit of pigtailing because then you have something called extra column band broadening. Versus a more normal looking column, 15 centimeter column, 4.6 mm ID, the retention time is much longer because L is proportional to the retention time, right? And also the resolution is proportional to the square root of N or square root of L, right? So here are the complexity of the relationship between L and N, which is the plate count, and resolution, right? So in most cases, we're interested in the resolution and the retention time, right? So here are the operating condition and what we have. Here is a set of slide from Waters Corporation, right? So this is also an important slide, demonstrating using a 5 centimeter column packed with 10 micron particle versus 1.6 micron particle, right? You can see 10, 5, 3 micron and 1.7, right? The difference, the retention time is not much different because that is defined by the column length, which is the same. However, the play count are very different, right? Because the play count here, we have 2,500, while the play count here, we have 15,000, right? And you can see the resolution, which is proportional to the square root of n, is also much better, right? The resolution between 2 and 3. Over here is 0.8, over here is 2.3. So a small particle is better, right? However, small particle also give you much higher back pressure because we are using a particle size which is 6 times smaller from 10 to 1.7, right? About 6 times smaller. The pressure drop is about 36 times larger, right? Very briefly on this very complex chromatogram, this is, I did this application myself. This is called it's a method development for an NCE or new chemical entity in which we did a force degradation. So I was supporting a product, which is the API here. When I do a force degradation, I have 2 degradation. I also have a process impurity, which is the aniline analog to the API. Now I have a choice. If I have a UHPLC, this is a UHPLC method development. If I use a 5 millimeter length column, coupled to very fast gradient time, a 6-minute gradient, 6-minute method, you can see that I can get very fast chromatography, and I have pretty good resolution, right? And I have a bunch of peaks towards the end, which seem to be 3 peaks over here, right? Now, in contrast, I can also use a much longer column and then much longer gradient time, right? So if I do that, you can see that I get much better resolution for this very complex sample, right? You can see even though it does not look too complex, it is very complex. If you look at the end of the 3 peaks, right? The last 2 peaks actually are a set of stereoisomers, which are separated by the longer column with longer gradient time, right? So with longer column, typically you use longer gradient time, and sometimes you're forced to use a smaller flow rate because the pressure is very high, right? The pressure is 11,000 psi, right? So definitely you have to sometimes scale the flow rate incommensurate to the pressure rating of the machine. You don't want to get too close to 15,000 psi. Okay, this is actually one of my last slides. The effective pore size, right? So here I'm doing a separation of protein. It's called fast protein chromatography. This reference came from 1989, right? So it's a pretty old reference. Published in Biochromatography, which is no longer active, right? This magazine is obsolete. And so I'm separating 6 proteins standard. 2 of the proteins are much larger. They're over 100 kilodalton protein, lactoperoxidase and amyloid glucosidase. So 5 and 6 are much more larger protein, right? If I use a 100 angstrom pore size material, this is actually a polymer column. They have no solanol or residual solanol, right? So they have very good peak shapes, but the pressure limit is only about 3,000 psi, right? So that's why we want to use silica. You can go to much higher pressure. You can see that for 100 angstrom, the larger protein are kind of much broader than the same column packed with 300 angstrom pore size. You can see this is much better. The reason being is that the large protein get entangled. It's called restricted diffusion, right? Once you get into the small pore, it gets stuck. It cannot get out, right? So it takes longer for it to diffuse out. So if you use a larger pore size, you have much better chromatography for the large protein, right? So by default, we use something much larger, particularly for glycoprotein, 300 angstrom to 1,000 angstrom to give us good chromatography performance. Okay, summary and conclusion, right? So the most common analytical column I would say that if I have a choice, if I need to do one column, it would be reverse phase column packed with C18 binder phase on a sub 3 micron porous silica. So that's kind of the standard default column. Our column length, typical length is 5 to 15 centimeter. The typical ID is 2.1 to 4.6 millimeter ID. Plate count, retention time, and resolution also increase with longer column length, but the proportionality is different, right? We mentioned that resolution is proportion to the square root of n or square root of L. I've been an advocate for 3 millimeter ID columns preferred for quality control applications. Okay, so today we use wholly porous or SPP silica particle with pore size of less than 200 angstrom for small molecule separation. We definitely use large pores, larger than 300 angstrom for macro molecules. Okay, so here are my references. The key references is chapter 3 of my own book over here, right? And there's also 2 references which you can download. They came from Ron Majors, which has been with Agilent for about 20 years. He is very active in HPLC column, probably the foremost expert in HPLC column today. So he wrote 2 articles for LCGC magazine, one on historical development and one on future need of HPLC and UHPLC tech. So those are some really important white papers on column trends. Here's the book by Uwe Neuer, who was the director of Waters for about 3 decades, right? So Uwe Neuer, as I mentioned, was a German chemical engineer. He did pass away about a decade ago, and he wrote a book which is still one of the a classic HPLC column book published in 1997.